Okay, thanks for coming. Welcome to that magical time of year called Finals Week. So ours is gonna come pretty fast, obviously, which is right starting next Wednesday, I suppose. So we don't have much time. So it's time to start reviewing. It's definitely showtime for us. So same format for this review as the rest. I'll go through the problems one by one that I posted, the first 20 anyway of the 34 that I have on that review. And then anytime you want me to stop and go over something again or just address anything related to that topic, just interrupt me with questions, and that's perfectly fine. And then, as I said, we'll finish the second part of this, the last 14 questions, in class on Monday at 4 p.m. All right, so here we go. The first one, taking a trip down memory lane back to some of the very first things we learned in this course, is related to mass ratios. So we saw that this was the first way that some of the early scientists characterized compounds and distinguished one from another and talked about their composition. So that's what this problem is dealing with. We have an iron sulfide compound. We're not told what the chemical formula is, but we know that the iron to sulfur mass ratio is 1.16 to 1. How many grams of sulfur are contained in 3.50 grams of this sample? So the first thing I have to do is recognize what the given information tells us. So if the mass ratio is 1.16 to 1, and that's the iron to sulfur ratio, that means what we have is 1.16 grams of iron for every 1 gram of sulfur that we have in the compound. So this is a normalized mass ratio. Now the other way to interpret this is also, remember that because of conservation of mass, we have the sum of the elemental masses is going to be equal to the mass of the compound. So another way to write this is that we have 1.16 grams of iron plus 1 gram of sulfur for every 2.16 grams of the iron sulfide. So if we just add those two together, 1.16 grams and 1 grams, that's 2.16. That tells us that out of the whole compound, 1.16 grams is iron and 1 gram is sulfur. And then from here, we can use either of these ratios to address what the problem is asking us. So here we're looking for the mass of sulfur that's in this sample. How many grams of sulfur are contained in 3.50 grams? We have 3.50 grams of our iron sulfide, which we don't, again, know the exact formula. It's some formula with iron and sulfur in it. And we're just going to use these mass ratios as a conversion factor. So we know from this information here that we have 1 gram of sulfur for every 2.16 grams of the compound. I'll write that generically as FeXSY to indicate that, again, we don't know the exact elemental composition, but we know the masses. And so again, that cancels out grams of the compound, allows us to convert into grams of sulfur, which comes out to 1.62. Okay? So this was sort of the first type of problem we did where we're using ratios as conversion factors, and in these cases it's going to be mass ratios, or in some cases mass percents, which would tell you the mass of an element out of 100 grams of the compound, which is another way that we can report the same information. So a few different ways of talking about this concept, but it's related to, again, the ratios of masses of elements out of the entire mass of the compound, and we can then use that to determine amounts of substance as we did here. So any questions on this topic? All right, so hopefully that rings a bell. We haven't seen that stuff in a while because we didn't really use mass ratios much after that, but that was one of the first things we did. The next few questions are going to talk about atomic structure and quantum mechanics and topics of that sort. So on the final exam, there's going to be, a few questions on each chapter. It's pretty much evenly distributed, as we'll see. And so when we're talking about some of the earliest stuff we did on atomic structure, this being in Adam's first course, as we call it, there's going to be a lot of different possible ways we could ask these things, but a lot of it just relates to things like this, subatomic particles, or the stuff we'll get into a little bit later, which is more of the electronic structure and energy levels and orbitals and things like that. So the first one here is just looking at the number of protons, electrons, and neutrons in the isotope where we gave you the full atomic symbol. So if we remember when we talked about atomic symbols way back when, we had this sort of generic layout for an atomic symbol. So it's a letter base, sorry, that should be a Z in our standard abbreviation, sorry. So it's a letter, which is the atomic symbol that tells you what the element is. It's a 1 or 2 letter symbol that identifies the element. And then we have this Z here, the lower number being the atomic number. And that tells us directly the number of protons in the nucleus. And as we kind of already talked about as well, this number is not always given in the symbol. So I gave it to you here. It's listed as 42 in this symbol, but it's not always going to be there because the name of the element tells you what the atomic number is if you have the periodic table in front of you. So if I hadn't told you that the atomic number was 42, we would look it up on the periodic table and find where that is, and I'll point that out in a second. The other number that's in the subscript, the superscript is A, and that's going to be our mass number. So this is always going to be a whole number, and it's just the sum of the number of protons plus neutrons for that isotope. So protons being labeled as P plus, neutrons N0. So that's going to be the mass number. So there's going to be potentially more than one mass number possible for a given element, where each of those different mass numbers characterizes one of the isotopes that differ with respect to their number of neutrons. And then finally, the last one, if we want to find the number of electrons, that's not going to be given to us directly in the atomic symbol, but it's going to be equal to the number of protons if we have a neutral element with no charge. And then, of course, if there's a net charge, we have to either add or subtract electrons to account for the net positive or negative charge that we have. So there's that one's not going to come directly from this. So then for this problem here, we have the symbol MO4692. So if we're looking for the number of protons and electrons, that comes from the lower number Z. So that's 42, and that's going to again be the number of protons, which in a neutral element is also equal to the number of electrons. So both protons and electrons for this isotope would be 42. And then finally, for the number of neutrons, we see that A, which is the mass number, is equal to 96. And that's equal to protons plus neutrons. So then if we want to find the number of neutrons, it's just going to be that number 96 minus the number of protons, which we already determined is 42. So this is going to have 54 neutrons. All right. So it's going to be 42 of each for protons and electrons, 54 neutrons, which corresponds to choice A. Now, as I said earlier, we wouldn't always give you the number Z. This atomic number won't necessarily be given directly in the formula. We could have also given this to you as just MO96, leaving that number out. So for that one, to figure out what Z would be, you have to go to the periodic table and find where MO is, which is going to be over here, number 42. So that number 42 that's right above the atomic symbol in the periodic table tells you what the atomic number is. So it might not always be there explicitly listed in the symbol, but if you go to the periodic table, you can figure out quickly what that would be. So that's where that number would come from if we didn't give it to you. Okay, any questions on atomic symbols or isotopes? All right, so hopefully a lot of this stuff seems simple compared to some of the things we've done more recently, and there are going to be questions on the final that are no more difficult than this. So don't assume that every question on the final is going to be something that's way out there or expecting you to really dig deep. A lot of them are going to be straightforward questions, just like I'm showing you here. A lot of the earlier topics especially are not too complex. All right, the next question deals with the relationship between frequency, energy, and wavelength. So we learned about electromagnetic radiation made up of what are called photons, little packets of energy that propagate through space. And we want to figure out the energy, frequency, or wavelength of one of those. There's relationships between all of those. So there's two equations that you're going to want to know for photons. So the first one is that the product of the wavelength and the frequency, lambda times nu as they're abbreviated, is equal to c, which is the speed of light. And so if you know either the wavelength or the frequency, you can find the other from this equation. And then the other equation that was important, which was for the energy of a photon, this was determined by Planck from the black body radiation experiment. If you're thinking about it in that context, it's just another constant h times the frequency. So both of these constants, h and c, are on the periodic table, so you wouldn't need to memorize them or anything. But you have these two equations, and then if we want to use this first equation, we can also rewrite the second equation as h times c over lambda. So we solve for frequency as c over lambda, and we can have another form of the equation, which is sometimes more convenient if you're working with wavelength instead of frequency. But any of these will work in any situation. You just have to know which one to use. So here we're going to use both of them because we're looking for both frequency and energy. So the first thing we need to do for these problems, though, is recognize that our fundamental constants c and h are in SI units, which the unit of length for the SI units is going to be meters, not nanometers. So here we have our wavelength in nanometers, which is a very common unit for wavelength, so we have to convert that to meters first. So the wavelength in meters is going to be that number, 485. And then remember that the conversion between meters and nanometers is there's 1 meter for every 10 to the 9th nanometers, or 10 to the minus 9th meters per 1 nanometer, however you prefer to think about that. So this wavelength in meters is going to be 4.85 times 10 to the minus 7. And then we can now use this number, we're using these two equations to figure out the other parameters. So the frequency here is, again, as we solve for it using this first equation, going to be equal to c divided by lambda. So c is the speed of light, which from our list of constants is 3 times 10 to the 8th. And then we divide that by the wavelength, which has to be in meters, as we said, 4.85 times 10 to the minus 7 meters. So that allows the meters to cancel out, and we get a number then that is 6.18 times 10 to the 14th. And if we're following units closely, this is inverse seconds, which is the same as hertz. So there's no difference there. We just write that as hertz, even though technically speaking it's inverse seconds. So that's the number for frequency. And then finally we can take that number and put it back in to calculate the energy of that photon. So E is equal to h nu, or alternatively we could have used this form of the equation with the wavelength that we had. But since we have frequency now calculated, we can take the other constant h, 6.626 times 10 to the minus 34 joules seconds, multiplied by the frequency that we just got. So then what we get for that is an answer in joules, 4.09 times 10 to the minus 19. Alright, so those are the two answers we're looking for. We have the frequency, which is 6.18 times 10 to the 14th. Energy of that photon is 4.09 times 10 to the minus 9, and that corresponds again to choice A. Now keep in mind, in the most recent iterations of these problems that we have in Blackboard, if you're calculating a number like this, we could ask you to enter it in scientific notation. We'd only have you do one number typically, not two, but if we were asking you to enter one of these numbers, remember that the format in Blackboard would have been, for example, for the frequency, 6.18 E14. So you would just write it, type it in like that. Follow the directions closely in Blackboard. I'm not opposed to going back and correcting things if you made just a silly formatting mistake and that's why you got it marked wrong, but it makes everyone's life a lot easier if you just do it right the first time and follow the directions that are in Blackboard. So that's how you would write it for exponentials in Blackboard, or occasionally what we'd also have you do is you would take the logarithm of one of these answers that has a large exponent in it, and then you report that in Blackboard, which makes it easier to type in the number, but you have to remember on your calculator how to take the log of whatever number you got, so adds a little bit of a complication for you guys. So remember, there's a few different ways we can report these answers in the case that they're not multiple choice questions, but either way, just follow the directions in Blackboard and you'll be fine. Alright, questions on this one or this topic in general? Alright, moving right along then. Alright, the next one is going to have some relationship to this one. We actually have two problems like this. I included two on this review because there's a couple places this could show up on the exam. So the first one is we're looking for the frequency of light emitted when a hydrogen atom undergoes a transition from the n equals 4 excited state to the first excited state. So whenever we're talking about transitions in hydrogen atoms, electrons going from between energy levels, either higher to lower or lower to higher, we think of the Bohr equation, which is that the difference in energy between those two energy levels is minus 2.18 times 10 to the minus 18 joules. Now technically there's a z squared term here, which is the number of protons in the nucleus. However, I'm 99.9% sure that all of the questions on the exams only involve hydrogen, where z is 1, so we can leave that out. And then you just have this difference here, 1 over the final value of n squared minus 1 over the initial value of n, where these are the two quantum numbers that the electron is moving between or transitioning between. So that's the equation we want to think about. And so what all we really need for these questions to get started is, what are the values of n that correspond to that we're going to put in here. And then, of course, once we have that number, what do we do with it? Because there's some different additional steps we can take, as we'll see in this problem and in a future problem. So the first thing we need is the different values of n. So the initial value where we're starting is pretty obvious. That's our initial value, ni, which is equal to 4. That's given to us directly. Now the next one is it's going from the n equals 4 state to the first excited state. So what's the final value of n going to be if it's going to the first excited state? I heard a 1. I like another one better, though. Any other guesses? 2. Okay, so nf is going to be 2, because remember that n equals 1 is what's called the ground state, and anything above that would be an excited state. So the first excited state would be n equals 2, the second excited state would be n equals 3. So if we said ground state, that would be n equals 1, but anytime we say excited state, we're talking about a number bigger than 1, and the first excited state, of course, being n equals 2, which is the next largest value of n beyond that. So that's going to be our final value of n, which is 2, because it's an excited state that we're going to. So those are the two values of n, and so then from there we just put those in, find the difference in energy. Now, it's important that you put these in the right order if we're calculating delta E specifically. That will change the sign, of course, of your answer. So we put the numbers in that way. The one we end up with is NF, the one we start with is N initial. And then what we get in this case is a negative number because the electron is going from higher energy to lower energy. So we get minus 4.09 times 10 to the minus 19 joules. So that means the electron is decreasing its energy by that much when it goes from 4 to 2. And then from there, of course, we have to think about what we do with this. So here we're looking for the frequency of light emitted. So whenever an electron goes from a higher energy to a lower energy state, it emits a photon, which has a wavelength of frequency that corresponds with the difference in energy. So the energy of the photon that's going to be produced in this process is just equal to the absolute value of the difference in energy. So again, this sign of delta E just tells you whether it's going from higher to lower energy or lower to higher. The energy of the photon is just going to be the absolute value of that number. So the photon that's either absorbed if it's going up in energy, or the photon that's emitted if it's coming down in energy. So we just take the negative sign off of that to get the energy of the photon. And as we just saw in the last problem, the energy of the photon is equal to h times the frequency. So if we're solving for frequency, we just take the energy of the photon and divide it by h. So that's the energy of our photon that we get determined from the Bohr equation. We divide that by the Planck's constant h. And then what I got was 6.17. This actually, coincidentally, I didn't expect this to be the case, but we got the same numbers as the last problem pretty much. But in a different way. We started with the Bohr equation to get this number. Okay? So it comes out to 6.17 times 10 to the 14th hertz. I didn't specify in this problem how to enter your answer, but as we talked about in the last one, there's a few different answer formats that you want to be prepared for. All right, so questions on this topic? Okay. We'll come back to another problem later on that's a little bit like that. All right, number 5 deals with electron configurations. Quick questions. Do your questions match mine? Yes? Okay, good, because I have 2 versions of this, and I always get paranoid that I'm going to give you guys the wrong version and then do a different one in here, and people are going to get confused and angry and all that stuff. So, good. We have the same questions, because this, I think, is a slightly updated one. So the atomic symbol and number of unpaired electrons for the element that has the following electron configuration. There's a couple of ways to approach these problems. They all involve using the periodic table, of course, when we're talking about electron configurations. So the first thing we have to do is identify the element. And the easy way to do this, we have the configuration. We know, which subshells are occupied, how many electrons they have. and that will relate to the position on the periodic table as I'll show you. But the easy way to do this is just figure out how many electrons that is. It's a neutral element, so that gives you the atomic number also, and then just identify it without thinking too hard about the configuration. So if we go to the periodic table, we have to figure out how many electrons there is. So, how many electrons do we have here? So the noble gas core krypton plus 5s2 plus 4d6, so that's the total number of electrons. You have to figure out how many electrons are in the core, which is abbreviated as krypton, those inner electrons that we don't specify. So we go to the periodic table, we see that krypton is atomic number 36, so we have 36 core electrons that are part of that configuration. And then we have 2 more electrons in the 5s subshell. We have 6 more in the 4d, and that gives us then a total of, is that 44? If I do math in my head, 42? No, 44. Jeez. Alright, so that's 44 electrons that are present in this element. Okay? 36 plus 8. So then we can just figure out from the periodic table which element has 44 electrons. So atomic number 44 is ruthenium. That's the number right there. So 44 is ruthenium. Now, if we wanted to relate that more directly to the configuration, which is an alternative and equally valid way of thinking about this, we saw that the configuration was given as krypton was our core electrons. Then we go to 5s2, so this is the 5s block, so that's 1 electron, 2 electrons. And then it was 4d6, I believe. So 1, 2, 3, 4, 5, 6 takes us to ruthenium. So either way, if you think about the full configuration or just look at the total number of electrons in there, you identify that ruthenium is the element of interest. So that's half of the answer. So that's going to be ruthenium is the atomic symbol. Now, unfortunately, we don't give partial credit in Blackboard, so this is a 2-part answer. So if we don't get the second part, you're not going to get this right either. So let's think about the second part, which is how many unpaired electrons there are. So to determine the number of unpaired electrons, all we have to think about are the partially filled subshells, the ones that don't have complete occupation with all the electrons paired in them. So the only partially filled subshell in this element is the 4d, which has 6 electrons. Remember, the d subshells can hold up to 10. So d6 would be a partially filled d. And then remember that we have 5 d orbitals in any d subshell. 2 ways to remember that. So this is our 4d orbitals. 2 ways to remember that. L equals 2. So that means there's going to be 2l plus 1, which is 5 orbitals. Or the other way to remember that, which also comes from the periodic table, is that if we go into the d subshell, there's the d block of the periodic table, in this case this row here that we're in, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements that are in any d block of the periodic table. If there's 10 elements, we can put 2 electrons per orbital. That means there's 5 orbitals. So a couple different ways of remembering that. Whenever you're in a d subshell, whether it be 3d, 4d, or 5d, you have 5 individual orbitals, and then we're going to fill these with the 6 electrons, and we have to follow Hund's rules and Pauli exclusion principle where to put these in the correct way. So we put the 6 electrons, we go, again, 1 electron in each orbital first. That's 1, 2, 3, 4, 5, and then we start pairing up, so the 6th electron would go there by convention. So that's sort of the partial electron configuration for the 4d. And we see that in here there's 4 unpaired electrons, 4 electrons that are spin up that don't have another one spin down with them. And so then the final answer for this would be the symbol is ruthenium, and the number of, it's 4, not 6. 6 is the total number of electrons, but the number of unpaired would be 4, so that would be the answer you would put in. So whenever you have to find number of unpaired electrons, you have to zoom in on those partially filled subshells and write out partial diagrams like this to figure out which of those electrons are paired or unpaired. And depending on which subshell you're looking at, whether it's an S, a P, a D, or possibly an F subshell, you're going to have different numbers of orbitals that have to get filled following Hund's rules and Pauli exclusion. Questions on that? Okay. On to number 6. Number 6 also deals with quantum numbers, which is sort of another way of defining orbitals and subshells and things of that sort. So before we get into this problem, what we're looking for is a valid set of quantum numbers for an F electron. And so remember that we have 4 quantum numbers possible, and all 4 of them are given here. So we abbreviate the first one as N, second one is L, third one is M sub L, and the last one is M sub S. So n is what's called the principal quantum number. And it's also helpful to think about what this tells us about the electrons. Remember that these quantum numbers are they're simple numbers, mostly integers, that tell us something that basically relate to the wave function for the electron. So the wave function comes from the Schrodinger equation, which is that horribly complicated equation for electronic energy levels and orbitals. But by using these quantum numbers, we can define things about that in a much simpler sense. And so these are all come from valid solutions to the Schrodinger equation, and there's 4 different parameters we're going to think about. So the first one is the principal quantum number, which tells us the size of the orbital, and also it contributes to the energy of the orbital. So size being the radial distribution, how far on average the electron is from the nucleus when it's in that orbital, and it's also contributing to the energy. The second quantum number, L, tells us the shape of the orbital. And as we'll see, very often we use letters instead of numbers to describe L. So S, P, D, and F tells us the value of L. And this tells us the shape of the orbital and also contributes to the energy if you have more than one electron. All right, an important distinction, not for this problem, but just to remember in general, is that for a one-electron element like hydrogen, as we saw with the Bohr equation that we already used, the energy only depends on n, doesn't depend on the other ones. For multi-electron atoms, so that be anything with more than one electron, the energy of the orbital or the electron depends on both n and l together. It's a combination of those two. So you have to remember that there's that distinction between single electron and multi-electron species. These last two here don't have anything to do with the energy of the electron, but they tell us some more things about the orbital. For this one, m sub l, the what's that one called? The magnetic quantum number. I'm drawing a blank on that. But anyway, it's the orientation of the orbital is what it tells you. So there's, in many cases, more than one orbital oriented in different directions in space, and this relates to that in some sense. And then finally, the last one, m sub s, is a property of the electron itself. It's the electron spin quantum number, which has either the values +1/2 or -1/2. Now, the other thing to remember then when we're talking about this problem, so these are the different quantum numbers we have, is sort of the relationships between them. So the first thing to think about is, if we look at this question here, we're looking for a valid set of quantum numbers for an F electron. So what does that letter F tell us about the quantum numbers, as we said? Yeah.
First one is 3.
So F tells us that there's a quantum number that's 3, but it's not the first one, it's the second one. So the letter S, P, D, or F tells us the value of the second quantum number L. So if we have an F electron, our L values are going to be either 0, 1, 2, or 3 for real atoms, and these correspond to the letters S, P, D, and F. So the letter F tells us that the value of L, the second quantum number in this case, as we list them in that order, is going to be 3. So we look for the ones that have L equals 3, the second one. So this one has the wrong value of L. This one also has the wrong value of L, so we can even exclude those without looking at the rest of those choices. So L has to be 3, the second number in these has to be 3, so that takes us down now to choices A, C, and D as possible answers. And then we're thinking now about the rules that relate to different quantum numbers. So we have L equals 3 in all of these, but now we have to see if they follow the rules that are present. So the first thing to remember is that the value of L, which again can be 0, 1, 2, and so on, the maximum value of L is n minus 1. Okay? So what that means is that if we have L equals 3, as we do for this situation, n has to be bigger than or equal to 4. The smallest value of n that's allowed would be 4 if your L value is 3. Okay? So we're kind of working backwards in the way we normally think about it. So that takes out choice A, because this 3, you can't have a n equals 3, L equals 3 combination. That's not an allowed combination. So in order for L equals to 3, n has to be 4, 5, 6, or anything above 4, but not anything below that. And then finally, the other rule to think about is the values for m sub L. So m sub L is the only one that can be negative of these first 3 quantum numbers. It goes from minus L, 0, all the way to plus L, which means that if L equals 3, m sub L has to be either minus 3, minus 2, minus 1, 0, 1, 2, or 3. So there's 7 allowed values of m sub L, but it spans negative 3 to positive 3. And that takes out choice D here, because in choice D, L is given as -4, which is not an allowed value either. So the only one that's left standing is choice C, which works because if L equals 3, N can be equal to 1, M sub L can be equal to -3, and then the fourth quantum number M sub S can be either +1/2 or -1/2, so that works as well. So that's going to be the only one then that's a set of 4 quantum numbers that identifies it as an F electron, meaning L equals 3, and then for the ones where L equals 3, follows the rules for the other 2 quantum numbers, N and M sub L, they all have these relationships. Okay, any questions? Yeah. Well, if you know, so you have to know one of the two, but the relationship again is this one here. So N can be equal to any positive integer. And then once you know what the value of N is, that specifies what the allowed values of L will be. So L starts at 0, 1, to all the way to N minus 1. So depending on what the value of N is, you're going to have different allowed values of L. So it works in both directions. We went the opposite way here because we knew the value of L and tried to find out which values of N would work. But if you know the value of N, you can also specify which values of L are possible. And again, it's not that L equals one of these values, is that L has all of those possible values depending on what the value of N is. Any questions beyond that? Okay, on to the next one then. All right, we're back to another hydrogen transition one, which actually I did a really bad job with this review, but I guess it'll still illustrate the concept. Same exact setup as last time, as it turns out. We have a transition in a hydrogen atom going from N equals 4 to N equals 2, but it's not the exact same question because this time we're looking for what is the wavelength of the photon that is absorbed or emitted. So the two things we need to think about are, is the photon absorbed or emitted in this process, and then once we know that, what would be the wavelength of that photon? All right, so keep in mind that what we're doing here is we have, if we want to draw a picture of it, we have our hydrogen energy levels, which get closer and closer together. And it says we're going from N equals 4 to N equals 2, so we're going from there, and the electron is going down to N equals 2. So whenever the electron goes from a higher energy level to a lower energy level, or from a larger value of N to a smaller value of N, that means that a photon is going to be emitted. So without even doing any of the math, we know that the photon is emitted because we're going from higher N to lower N. If we were going in the opposite direction, from lower N to higher N, from lower energy to higher energy, that would mean a photon had to be absorbed. So just by reading the values of N and the relative, the relationship between them, we can tell already that the photon is emitted during this process. So that can then cross out a couple of your answer choices because the photon won't be absorbed. And then we have to figure out, is the correct wavelength going to be 486 or 384 or possibly none of those? So now is where we have to set up the problem again with the Bohr equation to figure out what's the energy difference and then relate that to the wavelength of the photon. So same story as before. We start with the Bohr equation, delta E. We already saw this calculation, so this is a rehash. But keep in mind it's not impossible because it's randomized that you'll get two similar questions on your exam, so don't worry if that's the case. You shouldn't get two identical questions. I tried to make sure that wouldn't happen, but you could get two similar questions. So we put in the different values of N, and we get the same number that we got last time. So it's going to be 1 over 2 squared. All right, so that's just a rehash of a calculation we already did. But then we want to think about, again, what this number tells us. So the negative sign only tells us that the electron is going from a higher energy to a lower energy level, that it's losing energy during this process. But the energy of the photon that's produced, we said there's going to be a photon emitted during this process, is just equal to the absolute value of that. So photon energies are always positive. You can never have a negative energy for a photon. That's a nonsensical, non-physical situation. And that's going to be equal to hc over lambda. So last time we solved for frequency, this time we're going to solve for wavelength. So once we know what the energy of the photon is, we use one of those photon equations, either h times frequency or h times c over lambda. We use one of those to be able to then predict what the wavelength or frequency is. So lambda is going to be equal to h times c over the energy of the photon. So h and c are just constants, which you don't have to memorize because they're there for you. And c is at 3 times 10 to the 8th. And then the energy of the photon, again, is just the absolute value of this number here, the positive of the 4.09 times 10 to the minus 19. So this comes out to 4.86 times 10 to the minus 7 meters. And the answers are in nanometers, so we'd have to multiply this number by 10 to the 9th to see that it corresponds to 486 nanometers. Okay, so that corresponds then to choice B, which would be the correct one here. So the photon is emitted because the energy level of the electron is going down. It's going from n equals 4 to n equals 2. And then once we know that the photon is emitted, to calculate what that wavelength is, it's a two-step process that uses the Bohr equation, followed by one of those equations for the energy of the photon. Now, I guess I apologize slightly for having two very similar questions, but at the same time, this is some of the stuff that we haven't touched at all since the very beginning of the course. So I think it's good to review all the different possibilities of what we can do with that. So any questions on this topic? I think this is the last thing we'll see with Bohr model and quantum and all that stuff. This is a 4, I just can't write, as you guys know by now. So there you go. All right, any other questions? All right, so then what we're going to get into next are some of the trends in periodic in properties that come from the periodic table. So we've talked a little bit about electron configurations, and one of the importance of knowing the electron configuration is, we can talk about then some different relationships between properties. If we know the electron configuration and where the element is located in the periodic table, it can allow us to predict relative things about the size of the atom or the ionization energy, electron affinity, all those different things that we talked about. So this one here, we're looking for the largest atom or ion for the following list. Now we know that there's a periodic trend for size. We know that the size increases as you go from top to bottom of the periodic table. The size also increases as you go from right to left. And that's going to be a helpful trend when you're comparing just neutral elements, neutral atoms that have no charge at all. But here we have a bunch of things with different charges. Some of them are positive, some of them negative, one neutral in there. So before you start comparing these, you have to first think about how many electrons each of them has. Because again, the subshells that are occupied are going to be related to the radius of that atom or ion, the ones that are, the electrons that are furthest away from the nucleus define the size of that species. So we have to first think about how many electrons they have or what their configuration is. So we have calcium 2 plus, potassium plus, argon Cl minus, Br minus. If we go to the periodic table and find all of these, we see that calcium 2 plus has 18 electrons. So calcium has 20, we take away 2 to make it a positive charge. So the first one has 18 electrons. The second one is K plus, which also has 18 electrons. You just take 1 away from potassium. We have argon, which is still 18 electrons, and we have Cl minus, which also has 18 electrons. 17 is the number of electrons in chlorine. Add 1 to make it argon. So the first 4 answer choices all have the same number of electrons, all have the exact same electron configuration, which is that of argon. But then the last one, which is Br minus, down here, Br is atomic number 35. We add 1 electron to that, so Br minus would have 36 electrons. It'd have a whole additional subshell that's filled. So if we go back and list that out then, what we have for these ones is all of these have 18 electrons, which means they have the argon configuration. So that's the same as I said for all of those. So when you're comparing sizes, as I said, especially if there's different charges involved, it's helpful to think about the electron configuration first. So all of those have the same number of electrons. And then the last one here, as we said, has 36 electrons, so it's down 1 row in the periodic table, and has the configuration of krypton instead of argon. So there's some differences there in number of electrons. Now, in general, if you're comparing two things that are from two different rows of the periodic table, that have subshells that are filled from two different rows, the one that's, again, lower down is going to be the one that's larger. So I think if we're just looking for the largest one here, we can pretty much easily zoom in on Br minus as being the largest because, again, argon is going to have, the last filled subshell is going to be 3p6 for all of these, but then for krypton, we're filling the 4p subshell, so we're out a whole additional subshell from the nucleus farther away, so we'd expect this one to be bigger. Now, if we didn't realize that, we can again compare these one by one, and so get a little more detail into these relative sizes. If we look at choices A through D, these are all examples of isoelectronic species, which means they have the same number of electrons. And when we compare isoelectronic atoms and ions, remember that more negative charge correlates with a larger species. So that means the one that has the most positive charge is going to be the smallest. The neutral will be in the middle, and then out of these four, Cl minus would be the largest because it has the negative charge. And that's because it has fewer protons in the nucleus, so it doesn't pull the electrons as close to it as you would when you have, for example, calcium, which has 3 more electrons than chlorine. Sorry, 3 more protons than chlorine. They all have the same number of electrons. So this is the ranking of those four that have the same number of electrons. That goes by charge. And then if we're comparing Cl minus to Br minus, again, as we already sort of talked about, in Br minus, we're increasing from we're going from the 4th row to the 5th row of the periodic table. So that's going to be the order for Cl minus and Br minus because the atomic radius or ionic radius increases as we move down a group. So if you have two things that are right on top of each other, like chlorine and bromine, the one that's below is going to be the one that has the larger radius. So a couple different approaches to identify Br minus is clearly the one that's the largest of these three. If we have been asked to compare choices A through D, we could do that also, but that's going to be based on charge because all of them have the same number of electrons. Questions on this property or this one here? All right. Going on then to number 9, another periodic trend, which is ionization energy. So what we're looking for here is the trend in ionization energy. So again, this is, if we're looking at the periodic table, ionization energy is going to increase as we go bottom to top, and it's also going to increase as we go left to right. So that's the periodic trend. So basically, if we're looking for the smallest first ionization energy, we're looking for the element in these choices that's going to be the furthest to left and the furthest down on the periodic table, closest to the bottom left corner of the periodic table. So we can approach this sort of globally like that, just look at all of our choices and try to find the one that's closest to the bottom left corner, and that would work. I tend to prefer to compare things one at a time when I do these types of problems to really convince myself that I'm not missing something. And so what I'll do is I'll compare these different pairs just in the order that they're given. So we're looking for the smallest one. So if we compare sodium and boron, and we go to the periodic table and find those two, you see that Na is right here, number 11, boron is number 5. So boron is one row up from sodium and it's a few columns to the right. So for both those reasons, we would expect boron to have a larger ionization energy. It's above and to the right. So comparing those two, we can clearly see that boron has a larger ionization energy than sodium. So we're looking for the smallest one, so we can eliminate boron now from the answer choices. Now let's compare sodium and aluminum. So if we go to sodium and aluminum, they're in the same row of the periodic table. Aluminum is to the right. Now we talked in class on Wednesday about how there's some breaks in the trend, but there's no exception between group 1 and group 3. So magnesium would be higher than aluminum, but if we're comparing sodium and aluminum, we would still expect aluminum to be larger. So as you go left to right, there's a couple places where the trend breaks, as we said, but aluminum is still expected to be larger than sodium. So that we can eliminate aluminum. Sodium and magnesium, those two are right next to each other again. We expect magnesium to be even larger than we expect it to be, but certainly larger than sodium. As you go from group 1 to group 2, there's a pretty big jump in ionization energy across these two. So we still expect sodium and magnesium to have that order, so we can eliminate magnesium. And then finally comparing sodium to potassium. These two are pretty easy to compare because they're right on top of each other. And as we said, as we go down the periodic table, the ionization energy decreases. So sodium is going to be above potassium, which means sodium will be larger than potassium in terms of ionization energy. So that means the one that is left standing is potassium. So we didn't have to compare potassium to all the rest. We could just compare one at a time as I did there. So there's a few different ways to think about this. And I think it's pretty clear of these choices that the one that's furthest to the left and the furthest down is potassium. There's no ones that are, any further down or further to the left than potassium. So that's the clear one to pick here. But if it's a little bit less obvious, like I said, it's helpful to compare pairs of them, especially ones that have simple relationships. And to reiterate what I was saying before, if we compare sodium to magnesium to aluminum, we would expect magnesium to be larger than sodium and also larger than aluminum because there's that break in group 2. So these three would go in this order, but we're looking for the smallest one here, so we'd still pick sodium out of those three as being the smallest. But magnesium, again, there's a spike right there, group 2, so this one would be higher than both of its neighbors to the left and the right. So the trend that I showed here is not a smooth trend, as we said, but for this problem, I think we don't have to worry about the exceptions because it very clearly comes out to be potassium. That's the one that's the lowest. Okay, questions on ionization energies? Okay. Number 10, we're at the halfway point. You're getting there. For today, anyway. All right, so number 10, there's going to be some problems like this, and a lot of people get confused about, what the given information is telling us. So we have the formula for the oxide of gold is Au2O3. Which of the following is the formula for gold hydrogen carbonate, assuming the gold has the same charge? So really, when we have problems that are set up like this, where we give you the formula of one compound and ask you how does that then relate to the formula of another compound, the whole point of that is to tell you what the charge of the metal is, because it's going to be for, in many cases, a metal that's in the transition metal series where the charge is variable and you can't easily predict it based on its position in the periodic table. So we're going to use the given information about gold 2, Au2O3, to be able to figure out then what is the charge on the metal, the gold center. Then once we know the charge on the metal, we can then pair that with the second compound with this other anion to figure out what the formula for that would be. Okay? So in these compounds, we have to figure out what the charge in the metal is, and it's variable for the transition metals like gold. So we figure out first what the charge of the non-metal part is. So we have 3 oxygens, and if we go to the periodic table, which is always going to be our friend in these, oxygen is right here in group 6 in the third to last column of the periodic table. So that means for any element in this column, we expect it to gain 2 electrons and form a 2- anion when it forms ionic compounds. So oxygen is here, it gains 2 electrons to get noble gas configuration. So we would anticipate that the charge of the gold is going to be 2- each. We have 3 of them. So we have a total of 6 negative charges from the oxygens, and then to figure out what the positive charge would then be on the metal, we have 2 golds, and then they would each have to be 3+ to be able to balance out with the 6+ positive charge. So remember, the charges of the metals and the nonmetals have to balance and cancel out. So we know the nonmetal unambiguously is going to be 6- total charges. 3 2 minuses is a total of 6-. That leaves we need to have 6+ on the metal. 2 of them, meaning each of them are 3+. So now that we know that gold has a 3+ charge, we can figure out what would the formula of the compound be when we pair gold with a 3+ charge with the anion hydrogen carbonate. So this also asks us to remember our polyatomic anions and their charges. So if we remember, carbonate is CO3 2-. And I think it's pretty obvious from the answer choices it's going to be something with CO3. And if we have to remember that the charge of carbonate is 2-. But then for a lot of these polyatomic anions, especially the ones that have more than one negative charge, there's also versions of them that have hydrogen on them. So you put the word hydrogen out front. So for hydrogen carbonate, it's carbonate with an additional hydrogen or an additional H+. So that's going to be HCO3. And then the charge goes from -2 down to -1. So for a lot of the polyatomic anions, sulfate, phosphate, carbonate being three of the most obvious ones. If they have more than one negative charge, you can also add hydrogens to them to make another polyatomic anion that has a charge that's one less than that in magnitude. So we have, this is going to be the anion then that we're pairing with gold 3. So if we have HCO3 minus as our anion, we need to balance the charges. So again, the cheater way to do this is just to take the charges and make them the subscripts. But I think it's pretty obvious in this case, if we have 1 3 plus cation, we need to have 3 of the 1 minus anions to balance charge. So the correct formula would be gold with 3 hydrogen carbonates, and that's going to correspond then to choice C here. Alright, so to balance charges, that's going to be the correct ratio of gold to hydrogen carbonate. So if you've forgotten some of the polyatomic anions, we've used them a lot over and over again throughout the course, but some of the ones you may have forgotten, just take a moment to review those, because there will be some nomenclature problems or problems like this that ask you to be able to identify what the charge is of a certain polyatomic anion and then create a formula from that. All right, questions on this one? Yeah.
Can you explain the charge difference again between carbonate and then adding the hydrogen?
So what you're doing is you're adding formally an H plus to it. So you're taking CO3 2 minus, and then you're putting an H plus, which actually gets on one of the oxygens. We write the formula as HCO3, but in reality the hydrogen is bonded to oxygen, but it's an H plus formally, so it reduces the charge from -2 to -1. And then if you went and added a second hydrogen to that, you would get the neutral H2CO3, which we would call carbonic acid. But if there's still some negative charge left over, we would still classify that as a polyatomic anion, where the name just comes from the parent anion with hydrogen in front of it. Or alternatively, the other one that's you could be familiar with as well is if we have PO4 3 minus, we could also have, that's phosphate, we could have HPO4 2 minus, which is hydrogen phosphate, or H2PO4 1 minus. We've added 2 H pluses now, and that would be called dihydrogen phosphate. So whenever you have these polyatomic anions that have multiple negative charges, you can add H plus to them to make other anions that are related. If you add enough H pluses to balance the charge, then you'd have an acid, which is neutral and then named as an acid. All right, anything else? Yeah. So a few of these don't have hydrogen, so that one doesn't, yeah, so you could, yeah, B and E would be the two that don't have any hydrogen at all. So yeah, if you know that, if you see the name hydrogen in the name of an ionic compound especially, you know that it has hydrogen in it. So yeah, of course, if it doesn't have hydrogen, you can just get rid of it. So that's helpful, always a good strategy to eliminate answer choices, because if it comes down to a guessing game on any of these, put the odds in your favor as much as possible. Anything else? All right, on to number 11, our favorite. So we spared you on the midterm of having to calculate lattice energy, but now it's going to come up on the final, and there, just be prepared for it. There's going to be one question on lattice energy, two different flavors of questions. Either one like this, where you have to calculate lattice enthalpy, or another one. What other type would be to just compare lattice enthalpies between two different compounds. So there's kind of two different ways we could ask you about lattice enthalpy. So you might be lucky and not have to calculate it if you don't like doing that. But in this one, that's what we're going to do. So we have all this different information, and so there's a lot of ways to approach this. And some of you all have different strategies that you like, so I can certainly go over any of those. In most cases, the simplest way to do it is to just sort of remember the general equation. Remember that every question on the test is 1 point. Doesn't matter how long or hard it is, or how easy or simple it is. So like if it's going to take you 10 minutes to try to figure out how to do this, just try to do it the fastest way possible, in my opinion. If you're talking about sort of the game theory aspect of taking a test, if you just obviously you want to get it right because it's a test question, it still counts, but you don't want to. In general, it's bad strategy to spend too long on one question, because that just limits the amount of time you spend on other questions that may be easier and more straightforward for you, and you have a better chance of getting right if you spend the proper amount of time on them. So the fastest way to do these is to remember sort of a general equation that's going to work in just about every situation as long as it's not a sulfur-containing compound. And I'll tell you why that is in a second. So the general equation is you have an ionic compound with the formula Mx with subscripts that tell you how many of each metal and nonmetal you have. And then the equation for the lattice enthalpy, which is typically what we're going to have you solve for, is you start with the delta H of formation for the compound. So this is the only term that we're going to give you that's going to involve the compound itself. The rest of them are going to be enthalpy changes or energy changes that involve the individual atoms or ions. So the one that has the compound is delta H formation. That one you're never going to change the sign of it. You're never going to multiply it by anything. You're just going to use it exactly as it's given to you. Now the rest of the terms you have to account for how many of the metals and nonmetals there are. So there's going to be 2 terms for the metal, and we're going to multiply both of those by the subscript M. So you're going to take M and you're going to multiply that by the sublimation enthalpy, which is usually not going to be abbreviated like this, but this is the energy for going from metal solid to metal gas. And then the next term is going to be that same coefficient M multiplied by the ionization energy of the metal, which is, again, metal in the gas phase going to some cation plus electrons. So again, recognize the form of this being is, it'll sometimes be abbreviated as ionization energy, sometimes be given to you as the loss of electrons. So that's what ionization energy refers to. And then the last 2 terms are for the nonmetal. And these 2 you have to keep straight. So the first one we're going to take, actually I'm going to rewrite this as x, because this is how I did it in class. I don't want to confuse people. X over 2, number of nonmetals over 2 times the dissociation enthalpy, which is x2 going to 2x, if that's how we give it to you. And then you're going to have minus, sorry, I'll keep it as x to not be confusing, x times the electron affinity, which is, again, x going to some negative charge, either 1 or 2, depending on how many electrons you're adding. So we have to recognize the different steps and what they mean, but this is the order we put them in. Now the reason that sulfur won't work for this is because for sulfur you have S8, not S2. So for sulfur we would either give you this energy, which corresponds to the dissociation, so you have to multiply this by 1/8. If you're forming, or I guess x over 8, it'd always be 1/8, there's only going to be 1 sulfur in any of these compounds. Or we would give you the energy like this, 1/8 S8 going to just form 1S. So if your compound has 1S in the formula, which would be the case for any sulfide, you would either have to take the enthalpy for this multiplied by 1/8, or if we're just giving you the coefficients already multiplied by 1/8, you just use that directly. So be aware that sulfur is a little bit different if that comes up on your exam. So this is how we calculate lattice enthalpy, so now we can just start putting the numbers in. So for this compound here, M2X, the number of metals is 2, and the number of nonmetals is 1. So that's what we're going to multiply all of these steps by when we put these coefficients in. So we have the delta H of formation, which is for the compound itself, and we don't change that, minus 335. Then we're going to subtract 2 times the sublimation enthalpy, which is this one here. That's the amount of energy required to take solid metal and convert it into gas phase metal. So that's 79 kilojoules per mole. And again, we multiply it by 2 because there's 2 metals in the formula. We're going to subtract M times the ionization energy. So here the ionization energy we need is for the metal itself. So that's this term here for the metal, 525. And then we're going to subtract X over 2 times the dissociation enthalpy. We have 1 nonmetal X, we're going to multiply that term by 1/2. And that's going to be then this step here. This is going to be the dissociation as I've abbreviated it. And so as you see, the dissociation enthalpy is given in this case as X2 going to 2X's. We only have 1 X in the formula, so we're going to have to multiply this whole step by 1/2. And then we also multiply the delta H by 1/2. So that's where the 1/2 comes from. And that's going to be 1/2 times 178. Then finally we have 1x, so we're going to multiply the electron affinity by that number. The electron affinity in this case is a sum of 2 electron affinities because our nonmetal X is actually acquiring a 2- charge, but we would still use that number just as it's given to us. We don't ever change the sign of electron affinity or do anything differently that way. If we gave you the two electron affinities separately, you have to include both of them and add them together, but here we're giving it to you as a sum of two, so that's going to be just times 123. And so what this comes out to, if I put all the math in correctly, is minus 1755 kilojoules per mole. Now, one thing you'll notice in this problem, which is going to be something you'll want to be familiar with on the test, we gave you the ionization energy for X, but we didn't use it, and that's going to always be true. So remember, ionization energy refers to losing electrons. Our nonmetal X is gaining electrons. So if we throw that information in there, you just throw it right back out because you don't need it. You just need the ionization energy of the metal, not the nonmetal. So any questions on how we calculate that number? Now the last thing I want you to be aware of, just so you know, it'd be a shame that you do one of these problems almost all the way correctly and then stumble on this last step here. Keep in mind that lattice enthalpy is defined as this. It's this process. It's taking a metal plus a nonmetal. I'm writing it real generic here. But anyway, it's defined as taking the ions and combining them to make the compound. So it's not a perfectly balanced step. But remember that lattice enthalpy refers to the enthalpy change when ions, two ions, positive and negative, are combined to make an ionic compound. And this is going to be lattice enthalpy, which is always going to be exothermic, less than 0. Now in some of the problems it might ask you how much energy is required to take the ionic compound and break it up into its ions. The opposite process. So if we're asking for this process, what's the enthalpy change when the ionic compound is broken up into its ions? This is just the opposite of lattice enthalpy. So as we know from our studies of delta H in chapter 7, the delta H for this process is going to be the negative of the lattice enthalpy, which is always going to be greater than 0. So just make sure you have the correct sign on your answer. If we're asking you for lattice enthalpy specifically, you'll get a negative number, and it corresponds to the combination of the two ions to make the ionic compound. If we're asking you for the enthalpy change when you break up the compound into its ions, that's the opposite of lattice enthalpy, which means it would have a positive number. All right, so that also tests then again your knowledge and your understanding of enthalpy changes and how they relate when you reverse the order of a reaction and things like that. But it's the same exact calculation. Just recognize that your number would have to be a positive number if that's how we're asking to do it. Okay, questions on lattice enthalpy? Yeah. Yeah, because again, writing and talking is not my strong suit. When done simultaneously, especially. All right, so yeah, that would be a 2 there. Should be, of course, numerical once you put in the numbers. And I think everything else was written correctly. Anything else? All right, so these ones, we spared you on the third midterm. A lot of you still learn that stuff anyway, so hopefully you kind of know this stuff. And this is the type of problem that the only way to learn how to do it is to just keep practicing it, because there's not too many variations on this. They all have a lot of similarities to each other. The more you do them, the more comfortable you'll get with how we actually get from all this information to the final number. All right, and then go ahead.
What did you say the other variation of lattice energy question was?
So the other type of question about lattice energy would be we give you 2 or more compounds, 2 or more ionic compounds, and say which one has the highest or the lowest lattice enthalpy. And so for those comparisons, as we talked about in class, you first look at the charges of the ions. So the ions that have the highest charges are going to give you the highest lattice enthalpy. So if you're comparing like magnesium oxide that has a 2+ cation with a 2- anion, you expect that to have a higher lattice energy or a more negative lattice energy than something that has 1+ and 1- like sodium chloride. So the first thing you look at is charge. If 2 compounds have the same charges, to compare them, the lattice energy is inversely related to the distance between the ions, which comes from their ionic radii. So when comparing 2 compounds that have the same charges, the ones that have smaller ions are going to have a higher lattice enthalpy. The ones that have larger ions are going to have a smaller lattice enthalpy. So there's 2 things that you compare: charge and distance between the ions. So that's the other type of question you might come up on the exam. All right. All right, number 12 is going to deal with bonding types, which we revisited a little bit in chapter 9 that we just finished. So in number 12, we're looking for, we have 4 different substances here, and we're telling you what the bonding type is. All right, so the first one, FeCl3, ionic. So if you remember, what ionic bonding refers to is anytime we have a metal combined with a nonmetal. So metals being the elements that are on the left side of the periodic table, nonmetals being on the right. Fe is right here in the transition metal series, right in the middle, so that would still be classified as a metal, anything to the left of sort of this dividing line there. So it's a metal, chlorine is a nonmetal, so whenever you have a combination of metal with nonmetal, you would have ionic bonding. So that one's correct. Metal plus nonmetal is ionic. For this one here, copper is just a metal by itself. So if you don't have a nonmetal paired with a metal, that's not going to be ionic. Remember that for copper, you would have what's called metallic bonding. Anytime you just have a metal by itself, that's going to just be what we call metallic bonding. We didn't really learn about that back in chapter 3 when this stuff first came up. We talked about that much later in chapter 9. So that one's wrong because copper by itself would exhibit metallic and not ionic bonding. The next one is SOCl2 covalent bonding. So anytime we have nonmetals only, that's going to be covalent bonding. So if it's any combination of nonmetals, in this case SOCl2, so let's see if those are all nonmetals. So sulfur, oxygen, and chlorine, all clearly on the right side of the periodic table, so clearly all of those are nonmetals. So any combination of nonmetals you would expect to have covalent bonding, so that one is correct as well. And then the last one is AlCl3. So these are the 3 major types of bonding. Now let's see what kind AlCl3 should have. So aluminum and chlorine. Now hopefully we recognize that aluminum is a metal, because we've all used aluminum foil, and it's shiny and certainly looks like a metal. We see that aluminum here is on the right side of the periodic table, but it's to the left of that imaginary staircase. So aluminum is classified as a metal, even though it's in the P block of the periodic table. Most of these P block elements on the left side, except for boron, are classified as metals. So aluminum is a metal, chlorine is a nonmetal, so we would still classify this as ionic bonding. So that one's wrong, that should be ionic. That one should be metallic. So the 2 that are correct then, which is what this one's looking for, is 1 and 3. FeCl3 being ionic, SOCl2 being covalent. And that would be choice D. Alright, so again, 3 major bonding types that we covered, and being able to recognize which type a certain substance exhibits is just based on what kinds of elements make up that substance. Alright, anything want me to clarify on that? All right, now we're on to Lewis structures. My tablet reorients itself. There we go. All right, so we're looking for the Lewis structure of chlorite that obeys the octet rule, and we want to know what's the formal charge on the central atom. So there's a couple things that we have to do here. We have to first draw the Lewis structure of chlorite, and then we have to make sure that the Lewis structure that we draw obeys the octet rule. And so what we do then is we have to first count the number of electrons. So chlorite, reviewing our polyatomic anions, is ClO2 minus. So remember, with chlorine and oxygen, this is another good time to review nomenclature. With chlorine and oxygen, we have ClO minus, which is hypochlorite. ClO2 minus, which is chlorite. So the 2 that have fewer oxygens have the ITE ending, and then we have ClO3 minus, which is chlorate, and then ClO4 minus, which is perchlorate. So the per tells us that we have even more. So these could perhaps be some of the hardest ones to remember. The 4 different possibilities for chlorine and oxygen: hypochlorite, chlorite, chlorate, and perchlorate. And then also be aware that we have the same possibilities for the other halogens. So bromine and iodine, which are below chlorine, we have bromite and bromate, and per bromate we have iodate, all those possibilities as well, where we just replace chlorine with bromine or iodine. You have the same types of names as well. Which reminds me, do you guys know the formula for sodium hypobromite? Nah, bro, I don't know it. So that's like sodium hypobromite. So keep in mind that even though I think the table in your book might only cover the chlorine ones, chlorite and all those, but the same thing applies for bromine and iodine. You might occasionally come across those as well. So anyway, in this problem we're dealing with chlorite, which is ClO2 minus. So ClO2 minus is this formula here, so we have to count the valence electrons. So remember that the group number on the periodic table tells us how many valence electrons each element contributes. So we have a chlorine and 2 oxygens. And for the periodic table, chlorine is here in group 7A, so that tells us that there's going to be 7 valence electrons in chlorine. It would be the S2P5 valence electrons if we're keeping track of which ones those are. Oxygen's in group 6, so each oxygen will contribute 6 valence electrons. So that's how we count. We have 1 chlorine that contributes 7, 2 oxygens that each contribute 6, so that's another 12. Then we have to remember, whenever we have a minus charge or any sort of charge, we have to account for that in the number of electrons. So negative charge requires us to add 1 more electron. So in total, we expect this ion to have 20 valence electrons. And then when we draw the Lewis structure, that we account for all 20 of those before we stop. And then the steps for drawing a Lewis structure are to start with the least electronegative atom in the center, which is usually obvious. It's almost always the first atom in the formula. If it's not obvious, we'll specify for you which to put in the center. So that's going to be chlorine in the center. We start with single bonds to oxygens. And then we're going to complete the octets of the outer atoms first. So each outer atom should have 8 valence electrons surrounding it. It has 2 from the bonds, so we put 6 more on each of those to give them a total of 8. And at this point, we've used 16 electrons, 2 octets, 2 times 8 for the oxygens, and so that means we have 4 more. And whenever you have extra valence electrons beyond the octets of the outer atoms, then you put those on the central atom. So the last 4 electrons go onto the chlorine here. So that's initially where we would stop. And what this question asks is, we're looking for the Lewis structure that obeys the octet rule. So when we obey the octet rule, you want to have exactly 8 electrons on each element. So if that key phrase comes up in one of your problems, obeys the octet rule, we know that in some cases it's possible to exceed the octet rule, but anything that obeys the octet rule means it has exactly 8 electrons. So if we look at the oxygens, we know that we already completed their octets, and then the chlorine also now has 2 bonds, which is 4 electrons, and then 4 non-bonding electrons for a total of 8. So this structure here, we're obeying the octet rule, so we don't want to start drawing any more double bonds or anything like that. It's possible there could be a better structure that involves double bonding, but we don't want to do that here because we want to obey the octet rule. And now what it's asking for is what's the formal charge on the central atom. So for formal charge, we start with the number of valence electrons that the atom itself contributed, which is 7. So each chlorine contributes 7. We subtract from that the number of bonds that atom has. So chlorine has 2 single bonds, a total of 2 bonds. And then we subtract from that the number of non-bonding electrons in the structure. So our central atom has 1, 2, 3, 4 non-bonding electrons, those 2 lone pairs that we put on at the end. So that's 7 minus 2 minus 4. So in this particular structure, the central atom has a +1 formal charge. So the correct answer for this would be C. Now, what some of you probably recognize is that our central atom has a +1 formal charge. Both of our oxygens have -1 in this configuration. So it would be possible to draw a better Lewis structure that has 1 double bond between chlorine and oxygen to get rid of that formal charge. But here we wanted to make sure that we obey the octet rule, so we don't do any of that. We just stop at this one, which has exactly 8 electrons on chlorine, and figure out what will be the formal charge in that arrangement. All right, questions on this one? Or formal charges or Lewis structures in general? Okay, so then on to 14. This is a nomenclature question, aluminum 2 with 3 sulfurs, Al2S3. And we want to know what's the correct name for this. So again, for these types of problems with nomenclature, we also have to think about what type of compound it is, because ionic and covalent compounds have some slightly different rules for nomenclature. So the first element in this formula is Al, which is, as we said, a metal. We already saw that one in the previous problem. And then sulfur, which we've already seen a few times, is a nonmetal. So again, the combination of a metal with a nonmetal tells us that it's an ionic compound. And that means when we have an ionic compound, the key rule for nomenclature is that we don't have any prefixes at all. So then for ionic compounds, we just name the cation followed by the anion. So aluminum is the metal, it's the cation, and then the anion is sulfur. We have to change the ending to IDE for the anion. So we put the IDE ending on the anion. That's another part of the name that's important. But for ionic compounds, we don't use any prefixes to tell you how many of each one we have. So anything that has prefixes is out. So that has a prefix, that has a couple prefixes. So those two are out. This one doesn't have the IDE ending, so that one's out. And then finally this one, you don't want to put any numbers on there. So the only one that works is E, which is simply aluminum sulfide. So for ionic compounds, you don't specify numbers using prefixes. The only other part of the name that you sometimes will see is for cations that have variable charges, which includes most of the transition metals and a couple of the p-block metals like lead. You would have a number in parentheses, a Roman number in parentheses that tells you the charge of the metal. For aluminum, you don't need this because aluminum is always +3. There's no real exception to that. But for other metals, you might see a number in parentheses that tells you the charge, but that's the only other part of the formula or the name that you'd ever see for ionic compounds. Other than that, it's just the metal followed by the nonmetal. Yeah. Mostly for transition metals. I don't think your book covered p-block metals in detail anyways, we wouldn't show that, but most transition metals, you include Roman numerals. There's a couple where you don't. For example, zinc is always +2, so you don't have to include it. It wouldn't be wrong to include it. I mean, it's unnecessary, but not wrong to include it for other things besides those. But so zinc, you wouldn't typically include it. Silver, it's not common to include it either because silver is always +1 or just about always +1. For the rest of the transition metals, though, it's very common that you wouldn't have a Roman numeral because those have variable charges. The other ones, which we didn't really talk about much, they won't come up on the exams, are some of these p-block metals like indium, thallium, and lead down here. They can form also 2 different cations with 2 different charges that would be indicated in the name. But I don't think our book covered p-block cations, so we're not going to on the exam. Any other questions? Yeah. Yeah, so for covalent compounds, that's where the prefixes come into play. So if instead of Al2S3 it was, let's say, P2S3, which are 2 nonmetals, this would be, you put a prefix on both. Diphosphorus, tri, and then you'd still put the IDE ending on the second element. So the IDE ending occurs in both ionic and covalent, but the prefixes only occur in covalent compounds, and they tell you the number of each element. If there's only one of the first element, you leave the prefix out, but if there's more than one of the first element, you include prefixes on both. All right, anything else? All right, number 15. We're looking here now we're going on to talk about molecular structure. So which of the following molecules are linear? So we have CO2, H2O, xenon difluoride, and SO2. So keep in mind, all of these formulas have just 3 elements, 3 atoms in them, which means that there's only 2 choices for the geometry. It's either linear or bent. Those are the only 2 options when you have 3 atoms. So we have to figure out whether they're linear or bent in all of these. So again, we have to draw Lewis structures, and we have to then correlate that to a geometry. So CO2 is going to have a total of 16 valence electrons, 4 from carbon, 2 times 6 is 12, so you have 16 valence electrons in CO2. The best Lewis structure that we get for CO2 is this one here with 2 double bonds, and then 2 lone pairs on each oxygen. So that uses up all 16 of our valence electrons and completes the octets of all the atoms. And anytime you have no lone pairs on the central atoms, where it's just AX2, that would be one of the geometries that gives us a linear structure. So if there's no lone pairs, it's linear, so that's going to be CO2. If we go to H2O, hopefully by now we can draw this one in our sleep. So H2O is going to be, and I've already sort of suggested the geometry, but there's two lone pairs on the central atom. So if it's AX2E2, that's one of the ones that's going to be bent. So again, this is going to be it should be H2O, not HOO. Come on, get it together. There you go. Alright, so it's H2O, which is this structure. It's going to be bent. It's a tetrahedral electron group arrangement, so the bond angles are about 109.5, and so that's clearly not 180, so that makes it bent. If we go on to xenon difluoride, this is perhaps the trickiest one of the bunch. So there are some compounds that involve noble gases. When we count electrons for these, we have 8 from xenon, because it's a noble gas. We have 2 times 7 for fluorine. So I'm going a little bit fast with the Lewis structures, but we've already reviewed that, and I can slow down if you need me to. So for xenon difluoride, we start with, again, single bonds to the outer atoms. We complete the octets of the fluorines first. So now that we've used 16 electrons, we still have 6 more to go on the central atom, because it's 22 total. So we're going to put 3 lone pairs onto xenon. And this is the one that's perhaps the least intuitive or the hardest to remember. So we have 5 electron groups, which means they're going to be trigonal bipyramidal. And the 3 lone pairs all go on the triangle part, which leaves the fluorines up on the top and bottom. And so those are also going to be linear. So this is probably the least obvious linear structure. But when you have 3 lone pairs in the central atom with an AX2 structure, you would get linear geometry. So that one's also going to be linear. And then finally for SO2, when we count valence electrons for this, we have 3 group 6 elements. So we have 6 plus 2 more with 6 electrons. So 18 electrons. When we draw the Lewis structure for this, we get, after completing the octets on oxygens, we have, that's 16. We have still 2 more to put on the central atom. So it's an example of an AX2E structure. Now there would be a double bond in this, but for the purpose of predicting geometries, if we leave out some double bonds and things, that doesn't change the story. As long as you have the correct number of lone pair and bonded groups on the central atom, you'll get the right structure. So this is AX2E, which is bent. So this, I think, covers all of the possibilities when you have 3 atoms. As I said, those can be either linear or bent. If it's AX2, it's going to be linear. If it's AX2E or AX2E2, it's going to be bent. If it's AX2E3, which is this one, I didn't write it in, but it's AX2E3, 3 lone pairs on the central atom, that's linear. So for the 4 possibilities, 2 are linear, 2 are bent. Sort of drawing out the structures and knowing where they come from can be helpful for you to remember these, so you don't have to just do brute force memorization. But those are really, as I said, the only possibilities for 3 atoms is either linear or bent. You just have to know the different ones that come out as each. So choice B will be the correct one, CO2 and xenon difluoride being linear, the other 2 being nonlinear. All right, questions on VSEPR or anything related to this one? All right, 5 more, we're getting there. All right, number 16, we're saying which of the following has the greatest dipole moment? So before we start, figuring out how to compare dipole moments, the first thing we have to recognize is that anything that has a dipole moment is going to be polar. So if it's nonpolar, it has 0 dipole moment. That's the smallest possible dipole moment, which is 0. And then if it's polar, it will have a dipole moment. So when we look at these answer choices, the very first thing to do is look at all of them and decide which one's polar and which one's nonpolar. Anything that's nonpolar, we can eliminate. It has 0 dipole moment, so it can't be the greatest dipole moment of those choices. So we have CCl4, PF5O2, xenon difluoride, or xenon tetrafluoride in this case, and NF3. So CCl4, I'll skip a lot of the details of this, but if you draw the Lewis structure for CCl4, you get 4 single bonds to chlorine, lone pairs on each one. But the point being that this is an AX4 structure, And a helpful thing to remember on problems like this is if you have no lone pairs on the central atom, it's just AX whatever, assuming all the X's are the same, which they are, they're all 4 chlorines here. In all of these cases, these are going to be nonpolar. So 0 lone pairs on the central atom, all of the bond dipoles cancel out, it comes out as a nonpolar molecule. So no matter what X is, it'll be nonpolar. So then the same thing is going to apply for PF5. When we draw the Lewis structure for PF5, what we get is phosphorus in the center, 5 fluorines, a bunch of lone pairs on fluorine, but what really matters is whether or not there's lone pairs on the central atom. And what we find when we complete the octets and use up the correct number of electrons for PF5, we don't put any lone pairs on the central atom, so this is another one that's just AX5 with no E's, no lone pairs. So that would also be nonpolar because it has no lone pairs. Alright. The next one is O2. This one we shouldn't have to think about much at all because if it's a diatomic molecule, meaning there's only 2 atoms, there's 2 possibilities. It's either nonpolar or polar. If the 2 atoms are the same, it's nonpolar. If the 2 atoms are different, it's polar. So O2 is 2 of the same atom, which makes it nonpolar. So all 3 of these so far are nonpolar. And then xenon tetrafluoride, again, a slightly difficult one because it's one of these weird noble gas compounds. We don't see those a lot. For xenon tetrafluoride, the structure that we get is this here. So we have lone pairs on all the fluorines that we draw in. But once we do this, if we counted the electrons properly, we would see that there's still 4 more that go in the central atom. So this is an AX4E2 structure. And so this one we can't use a simple shortcut for because it has lone pairs, so we have to draw the structure and figure out if that's polar or nonpolar. AX4E2 is going to be an octahedral because it has 6 electron groups, 4 X's and 2 E's. So octahedral, remember, is sort of this square with one coming up and one coming out. And in this case, the lone pairs are going to go 180 degrees apart, which leaves the fluorines on the plane of a square, as the name tells us. So this is square planar, and this is going to be another example that gives us nonpolar, because in this case you have 2 fluorines that are 180 degrees apart from each other in each direction that cancel each other out in terms of their bond dipoles. So not as obvious as the other ones, but these ones, all the dipoles cancel out as well. And if you go back to the notes from that section of the course, which would have been towards the beginning of Chapter 4, I guess one of the earlier parts of Chapter 4, I sort of gave a summary table that summarizes the different AXE structures and whether they're polar or nonpolar. AX2E2 is an example of a nonpolar one where you get a square arrangement. And then finally the last one, NF3, what we get for this one we complete octets and fluorine. I sort of ran out of room there. But there's 1 lone pair left on the central atom. Let me redraw this so people don't get mad. So put the fluorine up there, and then there's a lone pair on the central atom. Okay, so that's NF3, 1 lone pair on the central atom, AX3E. And anytime there's 1 lone pair in the central atom, regardless of what everything else is, it's going to be polar. So if it's AX2E, AX3E, AX4E, or AX5E, if there's 1 lone pair, it will be polar. That's an easy and helpful one to remember. So that means the only one that's polar is AX3E, which means it must have the largest dipole moment. It's the only one that has a dipole moment at all. The rest of them are 0 dipole moments, nonpolar. All right, so when you're determining molecular polarity, it comes a lot from the shape. You have to have polar bonds. You have to have different electronegativity values for the atoms that are bonded together, but in addition to that, you have to take the shape into consideration to determine whether those individual bond polarities cancel out or whether they are, in fact, there is a net dipole moment in the molecule. All right, questions on polarity? Yeah? No, because, like, for example, if you compare PF5 to NF3, the PF bonds are more polar because phosphorus and fluorine have a larger difference in electronegativity than nitrogen and fluorine do. So this has greater bond polarity, but because it's in a trigonal bipyramidal arrangement, those individual bond dipoles all cancel each other out. So in that, the molecule itself has zero dipole. So if you're comparing just a bond, if I said which is the more polar bond, PF or NF, then it would come from electronegativity. But if we're talking about molecular polarity, the polarity of an entire molecule, you have to consider the shape as well, beyond just what the polarity of the bond is it's individually. Okay? Anything else? On to 17. So now we're talking about hybridization. So we have acetic acid, CH3COOH, and we want to know what is the hybridization of each carbon atom and how many sigma bonds are there. So the first thing let's do is figure out the hybridization. So we need to draw a good Lewis structure. For these organic compounds that have carbon, hydrogen, oxygen, and nitrogen, as we said, there's some shortcuts we can take. So we want to have, to complete the octets and minimize formal charges, for carbon we want to have 4 bonds and 0 lone pairs. For nitrogen, which is group 5, we want to have 3 bonds and 1 lone pair. So these can help you draw Lewis structures a little bit faster, especially for these more complex molecules that have chains of atoms and not a simple central atom structure like we dealt with before. Oxygen tends to have 2 of each, 2 bonds and 2 lone pairs. And then hydrogen, which is very often found in these organic molecules, of course just has 1 bond, nothing else. So hydrogen is the easy one. So if we start with CH3COOH, so remember that CH3, the hydrogens that come after the carbon are bonded to that carbon. So this carbon is going to be bonded to 3 hydrogens. And then it's also going to be bonded to the carbon next to it. So its 4th bond goes to carbon. And then COOH, it's helpful to remember that what this group refers to is you have a bond to oxygen, and then the other oxygen is bonded to the hydrogen. All right, so maybe not the most obvious Lewis structure, but this COOH group is a very common one that we should be familiar with, and it'll help us potentially in some of these. Now we just have to complete the structure. So for each oxygen we want to have 2 bonds and 2 lone pairs. So this oxygen only has a single bond. This carbon only has 3 bonds. So if we draw a double bond there, that satisfies the bonding for both of those. We add 2 lone pairs to oxygen. So that gives us, again, 2 bonds and 2 lone pairs for this oxygen and a total of 4 bonds for this carbon. And then this oxygen here already has 2 bonds, 1 to carbon, 1 to hydrogen. And we put the 2 lone pairs there. So that's the only way to draw that structure that sort of follows all of these rules and gives us complete octets and 0 formal charges. Now that we have the structure drawn out, we can figure out the hybridization. So I'm going to label the carbons 1 and 2 to keep them straight from each other. So carbon 1, again, the hybridization comes from the number of electron groups that are attached to that carbon. So this carbon has 4 electron groups, 4 things that are bonded to it, 3 hydrogens and a carbon. And so if it has 4 electron groups, we have to hybridize 4 orbitals. So carbon can hybridize an s orbital, and it can hybridize 3 p orbitals. For 4 electron groups, you have to hybridize all 4 of these, so we get sp3 for the first carbon. And then for the second carbon, what we have in this case is only 3 electron groups. So remember, an electron group is just something that's attached to that central atom. So for this carbon, we have 1, 2, 3 things. A bond to carbon, a bond to this oxygen, and then a double bond to that oxygen, but that still counts as just 1 electron group. So if we only have 3 electron groups, we only need to hybridize 3 orbitals. So we take the first 3 s and 2 p's, and that gives us sp2. So the 2 carbons in this have sp3 hybridization for the first, sp2 for the second. And the second part of the question is how many sigma and pi bonds are there? So what we have to remember for this is we've drawn out the structure. It has the correct bonding arrangement already shown. And then if we have a single bond, that's always going to be sigma, at least using the valence bond approach that we're using here. A double bond would be 1 of each, 1 sigma and 1 pi. So every type of bond has 1 sigma bond, and the rest would be pi. And then if we had a triple bond, which doesn't apply in this case, but could be a situation we'd have 1 sigma and then 2 pi's to make up the triple bond. So those are the 3 combinations that we would have for single, double, and triple. So for these bonds in here, we're trying to count sigma bonds. So there's a sigma, sigma, sigma. This double bond is a sigma and a pi, 1 sigma, 1 pi. a sigma there, and a sigma there. So if I count my number of sigmas, I get 1, 2, 3, 4, 5, 6, 7. So it's going to be 7 sigma bonds. So these will be the 3 parts of the answer, which I didn't specify a format for. I just wanted to get all that stuff covered in one question. So those would be, not likely you'd have to answer both of these in one single question, but that covers 2 important topics, hybridization and the types of bonds that form when we have this valence bond approach. All right, anything on that one? All right, 3 more. Number 18 now deals with MO theory. So when we're talking about simpler diatomic molecules, we have, in this case, molecular orbital theory that can help us answer some questions about bond order, number of unpaired electrons, and so on. So in this case, we want the bond order of the C2 2- anion. So the one thing that's helpful to remember is, well, you're going to have to remember for certain questions especially, is there's 2 different molecular orbital diagrams for p-block elements. So if we're talking about the first 3 elements in the p-block, boron, carbon, and nitrogen, remember we're going to mix together the 2s and the 2p orbitals to make molecular orbitals, and then they're going to come in this order for boron, carbon, nitrogen. So the sigma 2s is the lowest energy orbital, and then sigma star. So those are going to always be the 2 lowest energy orbitals. The bonding and the anti-bonding combination of the 2s's. And then for boron, carbon, nitrogen, in the p part of the diagram, the pi comes first. Pi is 2p, then sigma 2p. And then the top 2 orbitals are always the same, pi star and then sigma star. So for these types of elements, boron, carbon, nitrogen, whenever we form diatomic molecules that have those in them, the ordering for the p atomic orbital, or the molecular orbitals that come from that, is going to be pi sigma, bonding, bonding, anti-bonding, anti-bonding. Then the other type of diagram that we have, which is oxygen, fluorine, and neon, the second half of the p block, everything's the same down here, sigma and sigma star. Then when you get to the p orbitals, the sigma 2p comes first, and then pi 2p. And then the top 2 are also the same. So it's just those middle 2 orbitals that change their order when you go to the second half of the p block and you're drawing molecular orbital diagrams for those. So again, remember that those can change their order sometimes. Now the nice thing is, if you're just trying to determine bond order, it doesn't matter which diagram you use, you'll get the same bond order either way, because all you're switching is the ordering of 2 bonding orbitals. They're still both bonding, so they would both contribute to the bond order the same way. But if you want to answer questions about the number of unpaired electrons, especially in these earlier elements, you need to make sure that you put the pi orbitals first and then sigma when you're in this part of the diagram. So there's 2 different diagrams. Here we're talking about C2 2-. So what we're going to use is this left-hand diagram here. So for C2 2-, what we have to figure out is how many electrons there are. So each carbon from the periodic table it's in group 4. So each carbon is going to contribute 4 valence electrons. And then, so there's 2 times 4, and then we have 2 more from the negative charge. So this is going to have a total of 10 valence electrons. So from molecular orbital theory, once you know which diagram you're going to use, whether it's the left-hand diagram or the right-hand diagram, which is determined by which elements are in the formula, then you just have to fill it up with electrons from lowest to highest. So we have 10 electrons. We're going to go 2, 4, 5, 6, 7, 8, 9, 10. So we fill all of those orbitals, and then what we get is the bond order, which is what we're calculating here, is going to be 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. Alright, so the number of bonding electrons are the ones that are in orbitals that don't have a star next to them, the ones that are bonding orbitals. So for this we have these 2 down here, 4, 6, 8. So 8 of those 10 electrons, the sigma 2s, the pi 2p, and the sigma 2p electrons, all 8 of those are in bonding orbitals, so they increase the bond order. And then we subtract from that the number of electrons that are in anti-bonding orbitals. For the p-block elements, there will always be at least 2 anti-bonding electrons that are in the sigma star 2s, and in this case these are the only 2 that are filled with The only antibonding orbital that has any electrons in it is this one, so there's only 2 of those. The 2 numbers that you're subtracting would add up to be the total number of electrons. So if we have 10 valence electrons, in this case 8 are bonding, 2 are antibonding. And that gives us then a triple bond, which is the maximum bond order we can get for one of these p block elements. So the bond order for C2 2- is 3, which means that you would expect it to be a triple bond between the 2 carbon atoms in that dianion. All right. Anything you want me to rehash on that? Sure.
What is that versus
Neon. You can't really make a bond with neon, but if you were to draw a molecular orbital diagram with neon in it, it would follow this order here. So it goes. It's basically these 3 elements are the P1, P2, P3, the first 3 elements in the P block. These 3 elements are the second half, P4, P5, P6, and the order of those 2 orbitals switches at this position here. Now, if we had a heterodiatomic like NO, where it's 1 nitrogen, 1 oxygen, if it mattered for what we were asking, we would specify for you which order you would use, which of these diagrams you would use, because it's not easy to predict. If it doesn't matter, we might not tell you, but then you just use whichever one you want, and it'll give you the same answer. Especially, like I said, for bond order, it doesn't matter which of these you use. But for number of unpaired electrons, you do need to make sure you have the correct ordering of the orbitals to get that right. All right, anything else? Okay. All right, now we're into, if we're keeping track of where we are in the course, we've finished chapter 4 now in this review. The exam questions are roughly in order of the chapters, and that's what I have them here as well. So now we're into chapter 5. So the first topic we talked about in chapter 5 was atomic mass, which is the idea that the atomic mass that you get off the periodic table, which we use for calculations of moles and stuff that we're going to talk about a little bit later, that's a weighted average of all the individual isotope masses. So, most elements are composed of 2 or more isotopes, and if you take the weighted average of the isotope masses, that will give you the atomic mass that you would see on the periodic table and that you would use for different types of calculations that we've done. So what we have here is naturally occurring silver has 2 isotopes, 107 and 109. I gave you the masses of both. If the atomic mass is 107.87, what is the percent abundance of 107 silver? So which of the smaller isotope? So for these types of questions, we're asking you to either calculate atomic mass or calculate abundances from the atomic mass. Remember, there's just one simple equation that's related to that. So the atomic mass is the weighted average, which means it's the fractional abundance of one isotope, in this case 107 silver, times its mass, plus the fractional abundance of the second isotope, 109 silver, times its mass. All right. In this case, there's only 2 isotopes, so this is the formula. If there was 3 isotopes, 4 isotopes, you'd have to add in additional ones. So in this problem, what we're looking for is the percent abundance of silver, which is going to be the fractional abundance times 100. So this is going to be one of the unknowns that we want to find. We have a second one, which is the fractional abundance of 109. We don't know either of those right now. But then the other thing that's important is that the sum of the 2 fractional abundances will always be equal to 1. Or if you had more than 2 isotopes, the sum of all the fractional abundances equals 1, or the sum of all the percentages equals 100. That's true of any composition that's related to percentages or abundances. So then the 2 equations we get are the atomic mass for silver, which is 107.87, is equal to the mass of the first isotope, which is 106.905. Sorry, 106.905, times its abundance, which we're calling X, plus the mass of the second isotope, which is 108.905, times its abundance, which is Y. That's one equation. And then, as I said, the sum of the 2 abundances, X plus Y, will have to equal 1. So we have 2 equations with 2 unknowns. We're going to make a substitution here, which is that what we're solving for is X. We want the fractional abundance of 107. So the most direct way to get there is to replace Y with 1 minus X. So in terms of the unknown X that we're trying to solve for, Y is equal to 1 minus X. And so we plug that in and get a new expression. So X, which represents the fractional abundance of the 107 isotope. When we solve for X, we get 0.5175. And then the percent is going to be just that number times 100. So don't forget to convert fractions to percents or leave it as fractions that we asked for. So there's some, I've probably seen at least half a dozen or a dozen students this year where they missed a question like this or something that involves fractional abundances or percent abundances because they either converted to a percentage when they shouldn't have, or they forgot to do the last step, which is multiply by 100 if that's what we asked for. So if we ask for a percentage, you have to take your answer, which is a fraction, and multiply it by 100. So that's going to be 51.75% when we multiply that number by 100. And again, typically you would just enter the number, not the percentage, not the unit into Blackboard. But make sure you remember to multiply by 100. You won't get credit for the question otherwise. In these types of problems, it's helpful to make sure that your answer makes sense, of course, before you just slap it down there. So a couple things to look at. First of all, if you're asked to calculate the atomic mass, which we gave you here, so you weren't doing that here, but the atomic mass will always be somewhere in between the range of the isotope masses. So if you calculate an atomic mass that's either smaller than the smallest isotope mass or larger than the largest isotope mass, you definitely missed something. You're off on something. So check that out. And then for percentages, what we notice here is that our atomic mass, 107.87, which we're given in this case, is almost exactly halfway in between the 106.9 and the 108.9 isotope masses, right? This is pretty much the midpoint of those two. And if that's the case, then you would expect it to be close to 50%. If the atomic mass is much closer to the smaller isotope, you expect the atomic mass to be closer to the mass of the smaller isotope. Or if it was, so it depends on the relative percentage of the two, and you can sort of help yourself, kind of guess that your answer is at least reasonable before you put it down, if you want to do that. But this is the math, and again, there's only one equation that really relates to this concept, but we had to generate a second equation recognizing that the two fractions added together equals 1. All right, questions on that topic? All right, very last one for today is going to be our first calculation involving moles. So what we're looking for here is how many phosphorus atoms are found in 5 grams of calcium phosphate. So there's a few different things we need here to solve this problem. So we have mass of a substance. We're looking for number of atoms. So we should understand that this is some sort of calculation involving moles. We're going to go probably mass to moles and moles into Avogadro's number. So it's helpful to think about where we're going. But the information that we need is first we need the formula of the compound to get its molar mass. So for calcium phosphate, we have calcium 2 plus and we have PO4 3 minus are the two ions. And then to get the relative ratio of those two, again, we can take the charges and make them subscripts if we want. So we have to balance the charges, and to do that we need to have 3 calciums and we have 2 phosphates to balance the charges. So this is the correct formula, is calcium 3, PO4 2. If we're looking for the number of phosphorus atoms, number of phosphorus atoms, we know that we have 5 grams of substance. If we're going to relate that to the number of atoms, we need to know the number of moles first. So to get from grams to moles, as we know by now, we need to find the molar mass. So that wasn't given to you here. So to review molar mass calculations, we have 3 calciums. So we're going to take the atomic mass of calcium and multiply it by 3. The atomic masses come from the periodic table. So calcium is here. The atomic mass is the number below. So each calcium is 40.08. We have calcium, we have phosphorus, which is 30.97, and we have oxygen, which is 16. So those are the 3 elements. We have 3 calciums. Each one is 40.08. We have 2 phosphoruses, because we have 2 phosphates. Each one has 1, so the total of 2 phosphoruses, which are 30.97. And then we also have oxygen. We have 4 from each phosphate, but a total of 2 phosphates, which means we have 8 oxygens. Each one is 16 grams per mole. So when we add those together, we get a molar mass of 310.18. So that's going to allow us to then calculate the moles of this substance we have. We have 1 mole of calcium phosphate has a mass of 310.18 grams. But what we're looking for here is, again, the number of phosphorus atoms. So this is the moles of the whole thing we have, the whole formula unit. But if we want the number of phosphorus atoms, there's a couple ways we can approach this. But what I like to do is say, okay, if we have this 1 mole of this compound, how many moles of phosphorus do we have in there? So phosphorus, again, we said there's 2 of them in the 1 formula unit. So there's 2 phosphates, each one has 1 phosphorus. So in 1 mole of this compound, we're going to have 2 moles of phosphorus. So that gives us moles of phosphorus. And then once we have moles, if we're looking for the number of entities, the number of atoms in this case, we multiply that by Avogadro's number. So the definition of a mole is that there's 6.022 times 10 to the 23rd phosphorus atoms in 1 mole of phosphorus. So then moles of phosphorus cancel out, and that gives us the number of phosphorus atoms, which comes out to 1.94 times 10 to the 22nd. And then if we take the log of that, which is what we were asked to do to report this answer, it would come out to 22.29. So make sure you're familiar with whatever scientific calculator you're using, how to do the log function. But this is the answer that we get numerically. So it's a series of conversions. The step that the majority of people forget is this one here, to recognize that there's 2 moles of that element per 1 mole of compound. And keep in mind, there's going to be, we've used these mole calculations a lot now. We've used them for a lot more complicated operations. There's going to be some problems on the final that just say, if you have this massive substance, how many moles you have. Don't assume it's any more difficult than it is. This one's a little bit more complex because it has a few steps involved, but these are all conversions we've used many times now, so hopefully a few of these questions at least will be pretty straightforward for us, because it's stuff that we've been doing for so long. All right, that takes us to the end of today. We will finish up the rest of this in class on Monday, and I'll have this video posted as soon as I'm able to tonight.